In this project, I determined the thermal conductivity of a material called CFOAM. CFOAM is a competitive material for industrial heat transfer applications. Depicted is a sample size of about 126.85 millimeters squared that was given to me by Professor Brian Kinghorn here on BYU Idaho campus. It has interesting thermal conductivity properties. CFOAM is comparable to aluminum in its thermal conductivity. Aluminum has a thermal conductivity of about 167 watts per meters Kelvin, whereas the CFOAM is rated to have 140 to 180 watts per meters Kelvin. However, even though these are similar, CFOAM is 1/5 the weight of aluminum. This gives it an edge in industries such as aerospace, where weight is important. Thermal conductivity can be found using Fourier's law, which is that heat transfer equals the negative of thermal conductivity times the cross-sectional area multiplied by the temperature gradient in the spatial direction. The equation can then be solved for K. This was used to solve analytically for the thermal conductivity. This simple representation depicts the experiment where a hot plate, insulation, and the material were placed together as shown. Q represents the heat transfer from the hot plate. The insulation surrounding the material guaranteed that the heat transfer moved through the material in only one direction. T2 and T1 visualize the locations of the sensors used to measure the temperature difference. Thermistors were used in this experiment in two parallel voltage divider circuits. The first equation shown on the left illustrates the voltage divider equation, which is then solved for the thermistor resistance. The beta parameter form of the Steinhart-Hart equation was then used to convert the resistance of the thermistor into a temperature in Kelvin. So it turned out to be surprisingly difficult to measure the watts in this experiment. I used the kilowatt meter shown on the left to read the watts used by the hot plate. Before the end of the project, I had used 3 different hot plates. Each one would heat up and then cool down without maintaining steady state. I settled on using a hot plate from our kitchen. However, after reaching steady state, the kilowatt meter displayed a 0.3 watt reading. This was very low, but I decided to use it in my calculations. In order to learn more about this system and to test out whether unknown parameters in the energy balance equation can be estimated using parameter estimation techniques that we learned in our MA310 class, I used both recursive and batch estimation techniques to determine heat capacity, epsilon, and the heat transfer coefficient. Shown here is the energy balance equation, which includes direct heat transfer into the system, energy leaving through convection and radiation, and an energy storage term relating changes in temperature with time. This equation is then manipulated to match the form of y equals v transpose times beta, or theta. A low-pass filter was multiplied through to account for the derivative, shown here. The phi terms were then discretized individually for implementation in the algorithm. These equations are necessary for implementing the recursive estimation. They include a forgetting factor that determines how much the old data influences the new estimate. And it goes through and it estimates new values every time it iterates through the program. However, the results were inconclusive as the parameter estimations diverged wildly, resulting in a heat transfer coefficient and surface emissivity in 10 to the 4th power range and heat capacity in the 10 to the -3rd range. I knew these results were not valid, so I decided to move to batch estimation. In the batch estimation, I decided to leave out the energy storage term because if the system is steady state, perhaps the zero change in temperature was causing errors in the math. The pseudo-inverse of phi is shown here because phi was not a square matrix. This allowed me to solve for the unknown parameters in theta. This code shows my National Instruments BI used in the estimation. Using the averages of the temperature values, I calculated the thermal conductivity of the sample piece by using the equation shown previously. The results of the experiment are shown here with the average temperatures measured and the batch estimation of epsilon and heat transfer coefficient, as well as my analytical results for both epsilon and heat transfer coefficient, as well as the K value. I determined a K value of 0.0188, which turned out to be incredibly small, but this could be because of the Q value that I measured. The significance of these experiments and this method of parameter estimation It can be implemented in verifying manufacturers' material property claims. An issue occurred with NASA when, over a decade, it was sold faulty or fraudulent material that caused $700 million in damages and resulting in 2 satellite crashes. By using these software techniques, maybe it could be possible to estimate certain unknown parameters and thereby saving millions of dollars in the long run. Included here is the company information named CFOAM in Oceanside, California. Thank you.